So, complex plane. So, since the complex number is a pair of real numbers, we can represent it as a point on a plane. And this plane is called the complex plane or Argand diagram. This is a very natural way of representing complex numbers. The x-axis is the real number line, and any real number lies on the x-axis. Any pure imaginary number lies on the y-axis. So using simple trigonometry, we can see that we can relate the length, the modulus of a complex number, r, to x and y using Pythagoras, and also to x and y using trigonometry, where we've got the angle theta here. So this angle theta is known as the argument of a complex number, and is written like this: theta equals arg z. So, okay, the argument is not defined when z equals 0. Obviously, since it's an angle, there's lots of possible values, or infinitely many possible values of theta. What do we mean by that? Well, you could have theta in this case look something like 30, or you could add 360 and say it's 390 degrees, and so on. So you can always add 360 degrees, or if you're talking in radians, which is more usual, you can always add or subtract a multiple of 2 pi radians. So, but we give a special name to really the most natural value of theta, which is basically there's the one which lies between minus pi and pi radians, is called the principal argument. Okay, and that's sometimes denoted either with a theta sub p or by writing a capital A for arg. So as I said, the other possible values you get from just adding 2 pi n, where n is any integer. Now, the thing you have to watch out for is that you might think that theta, if I ask you to find theta in this case, you'll just say, okay, well, it's inverse tan y over x. The problem with the inverse tan formula is that it always gives an answer. If you put inverse tan something in your calculator, you always get an answer between plus 90 degrees and minus 90 degrees, or between plus pi by 2 and minus pi by 2. But obviously, if the complex number is somewhere pointing in this direction here, you're you need an answer which is between pi and pi by 2. So you do have to watch out for that. If you want, this looks very complicated, but basically you can always just draw a diagram and work out what theta should be. This in detail is what arg z is, the principal value of arg z for all the possibilities, depending on where x and y are. If x is greater than 0, then that corresponds to, obviously, this region here, where you're going to get between pi by 2 and minus pi by 2. That's when your calculator gives you the right answer when you do inverse tan. Otherwise, if the complex number is somewhere in this region here with a negative real part, then you have to do a bit more work, and you can't just use your calculator with inverse tan. You have to do a bit more thinking. Okay, but basically you should be able to work out what the angle is using trigonometry. Anyway, so the key lesson is that always think where the complex number is on the plane, and that way you should never get the wrong angle. Don't be lazy and just use a calculator, and don't bother remembering all of this either. You should be able to just draw a picture and work it out. Okay, so one of the most famous formulae is Euler's formula, which relates cos and sine to the base of natural logarithms e. So where does this come from? Well, one of the simplest ways to show it is you just expand the Maclaurin series for e to the x, where you replace x by I theta. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. If I replace the x by I to the theta, what do I get? Basically this, you've got I theta squared gives you the minus sign. I theta cubed gives you minus I theta to the power 4, I to the power 4 is 1 again, and so on. Then if you look at the real part of that, so the real part we expect to be cos theta, and indeed the real part of this is 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, which you recognize as the series for cos theta. The imaginary part, which we expect to be sine theta, is indeed, the imaginary part is theta minus theta cubed over 3 factorial, etc. So when you write a complex number in the form r times e to the I theta, where theta is the argument, we call this the polar form of the complex number. Okay, so as I think I mentioned before, you can think of adding complex numbers simply as adding vectors. It works in the same way. x1 and y1 are components of one vector, x2 and y2 are components of another vector. You just add the components and you get the sum of the complex numbers. And similarly with subtraction. So there's a famous triangle inequality which hopefully is obvious, that the modulus of, when you add two complex numbers, the modulus of the result, z1 plus z2, is always less than the lengths of the two complex numbers. This is illustrated here. You've got one complex number, another complex number, add them together, you just add the vectors z1 plus z2, and that's what z1 plus z2 looks like. This length here has to be less than or equal to the length of this side and this side of the triangle. So that's why it's called the triangle inequality. You can also show this one here, that it's got the length of z1 plus z2 has to be greater or equal to z1 minus z2, the length of those two. Again, that's really you can consider that by thinking of triangles again. Okay, I'll leave that for you to think about. It's difficult to describe without the blackboard. Okay, so complex conjugate operation that we talked about in the last video, this one here, where we just change I to minus I. Well, that corresponds simply to reflecting the complex number in the real axis. Okay, so it's illustrated here. Z1 looks like this, then Z1 star looks like this, Z2 looks like this, Z2 star looks like this. So just reflections. So, yes, more importantly is the geometrical sort of picture when we multiply two complex numbers together. And this is actually a very useful thing to know and remember. So, if we multiply two complex numbers in sort of Cartesian form and sort of component form like this, it's difficult to understand what this really means. But if we multiply two numbers in polar form, then we can instantly understand what's happening. So if we're multiplying Z1 and Z2, we convert it to polar form, R1 e to the I theta 1 times R2 e to the I theta 2, then we see that the answer we get is a complex number which has a modulus, a length of just the product of the lengths of the original two complex numbers. And more importantly, the argument, the angle, the direction it's pointing is simply the sum of the arguments of the two complex numbers. So basically, multiplying by a complex number, you effectively rotate the vector. So if you've got one vector, z1, and you multiply it by another vector, z2, then what you're doing is you're rotating the original vector z1 by an angle plus anti-clockwise angle θ2. Okay, and you're also changing its length, but essentially the operation of multiplying by a complex number is one of rotating by the argument. A consequence of this is that when you multiply complex numbers, then the length of the product is equal to the product of the lengths. Similarly, for division, when you divide by a complex number, it's easiest to understand if you write it in terms of polar form. Then you just divide the lengths, divide the moduli, and if you're dividing by z2, then it means you're subtracting. You're rotating in the other direction by θ2. And similarly, the length of a quotient is equal to the quotient of the lengths. Okay, so the modulus of ECI theta is 1. That's a useful thing to remember. Where does that come from? Well, just from this formula here, ECI theta. What's the length of this vector? Well, it's going to be cos squared plus sine squared, which is always equal to 1. So if you multiply a complex number by ECI theta, all you're doing, because it's length 1, is rotating it by theta in the complex plane. So you've got any complex number, z1, multiplying by theta gives you z1. It just rotates it by theta.